Today we're going to take a look at a special type of matrix called an inverse matrix, which is related to another type of matrix called an identity matrix, and how we can use the inverse and the identity to help us solve systems of equations. So this will be yet another way we can use matrices to solve systems of equations. So today we are solving systems with inverse matrices. And to set this up, we're going to talk about this guy called the identity matrix. And the identity matrix looks like a matrix that is in reduced row echelon form, but there's nothing else besides the ones and the zeros. So 2 by 2 identity matrix would have ones on the diagonal and zeros everywhere else. So it looks like reduced row echelon form, but it's only the ones and zeros, no extras. And depending on the size, a 3 by 3 matrix would look like this. 4 by 4 matrix, 5 by 5 matrix, ones down the diagonal of the square identity matrix. And what makes it an identity is if we take any matrix times the identity, say we take the matrix 2, -3, 4, 1, and multiply it by the identity matrix that matches its dimensions, let's take a look at what we get. First row, first column. So first row, first column is going to be 2 times 1 minus 3 times 0. And that's the first row, first column. First row, second column, that's going to be 2 times 0 minus 3 times 1. That's first row, second column. Now underneath that, we're going to do second row, first column. So second row, first column. That's 4 times 1 plus 1 times 0. That's our second row, first column. And finally, the second row, second column, where we have 4 times 0 plus 1 times 1. And what you notice about all of these is when we multiply by 0, I didn't finish my highlighting there. That was the green and that was the pink. What you notice about all of these is when we multiply by 0, that 0 part goes to 0, so those are all gone. So all that's left in this matrix is 2 times 1, -3 times 1, 4 times 1, and 1 times 1. And notice when we multiplied by the identity matrix, we get the same answer back. It does not change. This is the same as multiplying something by 1. 5 times 1, you get 5 again. It doesn't change the value. Multiplying by the identity matrix will give you that same matrix back again. It does not change the value. Now what's interesting is when we multiply some matrices, like for example, if we multiply the matrix 7, 2, 3, 1 by the matrix 1, -2, -3, 7, let's see what we get here. Again, following the same logic, we've got first row, first column. So that's going to be, that's going to be 7 times 1 plus 2 times -3. In the first row, second column, we've got 7 times -2 plus 2 times 7. keeping with my highlighting. First row, first column. First row, second column. Second row, second column. That's going to be 3 times 1 plus 1 times negative 3. And that's our second row, second column. And I'm sorry, second row, first column. And finally, second row, second column. Working that out, it's going to be 3 times negative 2 plus 1 times 7. And when we simplify this, we end up with 7 minus 6 is 1. Negative 14 plus 14 is 0. 3 minus 3 is 0. Negative 6 plus 7 is 1. And we end up with the identity matrix. This is important. These two matrices that we just multiplied together are what we call inverse matrices. Inverse matrices are two matrices that multiply to the identity. So if they multiply together, the product's the identity. Those two matrices are said to be inverses. So how do we go about finding an inverse matrix? The way we find an inverse is we are going to set up an augmented matrix. And in this augmented matrix, we're first going to put the matrix we want to find its inverse. We'll call it matrix A. We're looking for A's inverse. And then the second half of the augmented matrix, we're going to put the matching identity matrix. Then we will put A, matrix A, in reduced row echelon form. So now it is the identity on the left side, and when we do that, we will have the inverse matrix on the right side. So let's take a look at how we can do that, how we can find an inverse. Starting with a simple example, we'll start with a 2 by 2, and then we'll get to a more interesting 3 by 3 example. So we've got negative 2, 3, negative 5, 7, and we want to find the inverse. Well, what we're going to do to find the inverse is we're going to set up the augmented matrix, negative 2, 3, negative 5, 7. And the other half is the matching identity, 1, 0, 0, 1. Then we can go through our row operations to make the left side into the identity. When we do, the right side will be the inverse. We know to start finding an identity, we want a 1 in that top left spot. So we have to take row 1 and multiply it by the reciprocal of negative 2, which is negative 1/2, to get our new row 1. So negative half, so we got negative times a negative is a positive. 2 over 2 is 1. Then we have negative 3/2. Negative times a positive is negative 1/2, and 0 times a half is 0. Bottom row unchanged, negative 5, 7, 0, 1. Now that we've got that 1 on the pivot point, we want everything above and below to be a 0. So we need to multiply by the opposite of negative 5, which is a positive 5. So we'll take row 1, multiply by a positive 5, add it to row 2 to get the new row 2. So row 1 is unchanged, 1, negative 3/2, negative 1/2, 0. When we multiply row 1 by 5, we get 1 times 5 is 5. Negative 3 times 5 is negative 15 over 2. Negative 1 times 5 is negative 5 over 2. And 0 times 5 is 0. we might need to get some common denominators. 7 is 14 over 2 to help us out with the addition. Negative 5 and 5 is 0. 14 minus 15 is negative 1/2. Then we have negative 5 halves, and 1 plus 0 is 1. The first row is set. Now we have to get the second row, and we need to do that by getting a 1 in the bottom right corner. We do that by multiplying by the reciprocal of negative 1/2, which is negative 2, times row 2 to get our new row 2. When we do that, we get this top row is unchanged. 1, negative 3 halves, negative 1/2, 0. The bottom row, when we multiply by negative 2, is 0, 1. Negative 5 times negative 2 is positive 10 over 2, which is 5. And 1 times negative 2 is negative 2. Now we just need to get a 0 above it, and we will have that reduced row echelon form, or the identity, on the left. We do that by multiplying by the opposite, which would be a positive 3 halves, times row 2, add it to row 1 to get the new row 1. And when we do that, we'll have the bottom row unchanged, 0, 1, 5, negative 2. In the top, multiplying by 3 halves, anything times 0 is 0. 3 halves times 1 is 3 halves. 5 times 3 halves is 15 halves. And negative 2 times 3 halves is negative 6 over 2, which reduces to negative 3. So when we add 0 and 1, negative 3 halves and positive 3 halves is 0. 15 minus 1 is 14 halves, which reduces to 7. And 0 and negative 3 is negative 3. So if that's the case, now that we're in reduced row echelon form on the left, we have the identity on the left, the inverse is this right side. So the inverse then is the matrix 7, negative 3, 5, negative 2. If we wanted to verify that this was the inverse, we could multiply it by the original matrix. Up here at the top, the original matrix was negative 2, 3, negative 5, 7. And if it really is the inverse, it should give us the identity as a solution. And sure enough, it does. We'll go through this really quick. First row, first column, 7 times negative 2 minus 3 times negative 5. Then we have first row, second column, 7 times 3 minus 3 times 7. Then we have second row, first column, 5 times negative 2 minus 2 times negative 5. And finally, second row, second column, 5 times 3 minus 2 times 7. And when we simplify this, sure enough, we get negative 14 plus 15 is 1. 21 minus 21 is 0. Negative 10 plus 10 is 0. And 15 minus 14 is 1. Sure enough, we get the identity. So we have found the inverse matrix. So this is our final answer, the inverse matrix 7, negative 3, 5, negative 2. Pretty straightforward. It's the exact same process with a 3 by 3 matrix. Let's try one. Let's find the inverse of the matrix. 0, negative 2, 1, 2, 3, 0, 1, negative 1, 1. and we're going to find the inverse of this matrix. Same exact process. We're going to stick it right next to the identity. So 0, negative 2, 1, 2, 3, 0, 1, negative 1, 1. Augmented this time with a 3 by 3 identity with 1s down the diagonal, 0s everywhere else. Our first goal is to get a 1 in the top left corner. It's a 0. That's kind of difficult. You can't multiply 0 by anything and get 1. But what I also notice is this bottom left entry is already a 1. So if I were to swap those rows, it would give me the 1 in the top left that I want. So that's what I'm going to do, is I'm going to swap row 1 and row 3. So row 1 swapping with row 3. I don't think I'm going to have enough space to write 2 matrices on one line, so we're going to use up a lot of white space here. So swapping row 1 and row 3, now the top row is 1, negative 1, 1, 0, 0, 1. The middle row is still the same, 2, 3, 0, 0, 1, 0. And the bottom row is now 0, negative 2, 1, 1, 0, 0. Now that we've got our 1, we want to get zeros everywhere else. The bottom left's already a 0. That's nice. We only have to fix the center left, that 2. So the opposite of 2 is negative 2 is what we multiply the pivot, row 1, by, and add it to row 2 to get our new row 2. When we do that, the top row is unchanged. 1, negative 1, 1, 0, 0, 1. Multiplying by negative 2, so we have negative 2. Negative 1 times negative 2 is 2. 1 times negative 2, 0 times negative 2, 0 times negative 2, and 1 times negative 2. Adding those together, we get 0. 3 plus 2 is 5. 0 minus 2 is negative 2. 0. 0 plus 1 is 1. And 0 and negative 2 is negative 2. The bottom row is unchanged. It already had the 0 we wanted, so I'll just copy it down. And now we're ready to move on to our next pivot point. Our next pivot point is the 5. We need that 5 to be a 1. The way we get it there is multiplying by the reciprocal. We'll take 1/5 of row 2 to get our new row 2. When we do that, the top row is unchanged. 1, negative 1, 1, 0, 0, 1. Take dividing everything by 5, we get 0. 5 over 5 is 1. Negative 2/5, 0, 1/5, and negative 2/5. And the bottom row is unchanged. 0, negative 2, 1, 1, 0, 0. Now that we got the 1 we want zeros everywhere else. So we have to take the first row. It needs to be multiplied by the opposite. It's going to be multiplied by 1. We'll take 1 times row 2 and add it to row 1 to get our new row 1. The opposite of negative 2 is positive 2 times the pivot in row 2. We'll add it to row 3 to get our new row 3. When we do that, we get our new matrix. The top row, we're just multiplying the pivot row, the center row, by 1. So we have 0, 1, negative 2/5, 0, 1/5, and negative 2/5. A couple that we might need to get a common denominator on. The 1 is 5/5 both times. That'll help us with our adding and subtracting. So 0 plus 1 is 1. Negative 1 and 1 is 0. 5 minus 2 is 3/5. 0 plus 1/5 is 1/5. And 5 minus 2 is 3/5. The center row is unchanged. 0, 1, negative 2/5, 0, 1/5, negative 2/5. The bottom row, we're multiplying the pivot center row by 2. So when we multiply by 2, 0 times 2 is 0. 1 times 2 is 2. Negative 2 times 2 is negative 4 fifths. 0 times 2 is 0. 1 times 2 is 2 fifths. And negative 2 times 2 is negative 4 fifths. Again, the common denominator we need, the only time we need real and 1 really is the 1 is 5 fifths. So, adding that together, 0 plus 0 is 0. Negative 2 and 2 is 0. 5 minus 4 is 1 fifth. 1 and 0 is 1. 2 fifths and 0 is 2 fifths. And 0 minus 4 fifths is negative 4 fifths. Our second row is done. Now we just need our third row, starting with the pivot point at 1 fifth. It needs to be a 1. We multiply by the reciprocal, which is 5, times row 3. We'll not add it, we're just going to replace it. Erase. Here we go. 5 times row 3 to get our new row 3. So the top two rows are unchanged. 1, 0, 3 fifths, 0, 1 fifth, 3 fifths, 0, 1, negative 2 fifths, 0, 1 fifth, negative 2 fifths. Now, third row, multiplying by 5, gives us 0, 0, 1. 5 fifths is 1. 1 times 5 is 5. 2 times 5 is 10 fifths, which reduces to 2. And negative 20 fifths reduces to negative 4. Now we're ready to get the zeros above it. We do that by multiplying the pivot third row by the opposites. So the first row has 3 fifths, so we'll multiply by negative 3 fifths times the pivot row 3. Add it to our row 1 to get our new row 1. In the center row, the opposite of negative 2 fifths is positive 2 fifths times the pivot row 3, and we'll add it to row 2 to get our new row 2. So let's see what that gives us. The first row we are multiplying by negative 3 fifths, so 0 times negative 3 fifths is 0. 0 times negative 3 fifths is 0. 1 times negative 3 fifths is negative 3 fifths. 5 times negative 3 is negative 15 over 5 is negative 3, or we could have reduced out the 5s. 2 times negative 3 is negative 6 fifths. Negative 4 times negative 3 is positive 12 fifths. So when we add those together, we get 1, 0, 0. Like we expect. On the second half, 0 minus 3 is negative 3. 1 minus 6 is negative 5 fifths, which reduces to negative 1. 12 and 3, that's 15 fifths, which reduces to 3. The second row, whoops, we need to do our multiplying first. Multiplying by 2 fifths this time. 0 times anything is 0. 0 times anything is 0. 1 times 2 fifths is 2 fifths. 5 times 2 is 10 fifths, which reduces to 2. 2 times 2 is 4 fifths. Negative 4 times 2 is negative 8 fifths. And so what does that give us in the second row? 0 and 0 is 0. 0 and 1 is 1. Negative 2 fifths and 2 fifths is 0. 0 and 2 is 2. 4 and 1 is 5 fifths. 5 fifths reduces to 1. Negative 8 and negative 2 is negative 10 fifths, which reduces to negative 2. The third row is unchanged, so it's just 0, 0, 1, 5, 2, negative 4. And now we're ready to verify our answer, because we have the identity on the left, the inverse must be on the right. So the inverse is negative 3, negative 1, 3, 2, 1, negative 2, and 5, 2, negative 4. And again, we can verify this is the inverse if we were to multiply it by the original problem. And if you look up on your notes, you'll see that the original problem is 0, -2, 1, 2, 3, 0, and 1, -1, 1. So let's multiply this and see if we do, in fact, get the identity like we should. First row, first column, we've got -3 times 0 minus 1 times 2 plus 3 times 1. First row, second column, we've got -3 times -2 minus 1 times 3 plus 3 times -1. First row, third column, we've got -3 times 1 minus 1 times 0 plus 3 times 0. Close off the matrix. Continuing on in the second row then, second row, first column, we've got 2 times 0 plus 1 times -2 minus 2 times 1. Then we have second row, second column, we've got 2 times -2 plus 1 times 3 minus 2 times -1. Continuing on, we've got second row, third column, 2 times 1 plus 1 times 0 minus 2 times 1. Finally, in the third row, first column, this is becoming very colorful. 5 times 0 plus 2 times 2 minus 4 times 1. I'm running out of colors. Third row, second column, 5 times -2 plus 2 times 3 minus 4 times -1. And finally, I'm going to repeat the blue because I'm out of colors. Third row, third column, 5 times 1 plus 2 times 0 minus 4 times 1. Hopefully, when we simplify this mess, we will get the identity. In the top left, we've got 0 minus 2 plus 3 is 1. Going across, we got 6 minus 3 is 0. -3 plus 0 plus 3 is 0. 0 minus 2 minus 2. What happened there? Whoops. I got a little error here. I was moving too fast. Right there. Just showing what I did here. We multiplied in the center the 1 times the 2, and I wrote -2. That should be 1 times +2 there. Sorry, moving too fast there. So when we add there, we do get 2 minus 2 is 0. In the center, -4 plus 3 plus 2 is 1. On the right, 2 plus 0 minus 2 is 0. Bottom row, 0 plus 4 minus 4 is 0. -10 plus 6 plus 4 is 0. And 5 plus 0 minus 4 is 1. We do get the identity. That tells us our answer is correct. And if you can see our answer inside all of this color, whoops, that was a 1 I just deleted accidentally, and a 2. So our answer then is that inverse that we originally found. We did have the correct answer. So what's the big idea with inverses? What's the big deal? How do they help us? Why do we stress them? Well, the reason we stress them is because we can use inverse matrices to solve a system of equations with the inverse. This is now our fifth way we're going to see to solve systems. We saw graphing, we saw substitution, we saw elimination, we saw reduced row echelon form, and now we are seeing inverses. And the idea behind inverses, behind using an inverse to solve is similar to taking 2/3 x equals 6 and trying to solve this. Well, the way we solve 2/3 x equals 6 is we multiply both sides by the reciprocal. You could think about it as we're multiplying by the inverse of 2/3. We're multiplying both sides by 3/2 because the inverse goes to 1, the identity, or just x. And 6 times 3 is 18, over 2 is 9. And we get our solution. It's much the same idea with matrices. With a matrix, if we have some matrix A, think about this as matrix notation now of a system, times the variable matrix is equal to the solution matrix, we need to multiply by the inverse of A. We'll write A inverse on the left, and with matrices, left and right makes a big difference. So we're multiplying by A inverse on the left, because A times A inverse, we know anything times its inverse is the identity matrix. We use I for the identity times x equals A inverse B. Well, anything times the identity on the left side is just the thing we started with. So x, the solution matrix, is equal to A inverse B. Which means if we can find the inverse of the coefficient matrix, and multiply it by the solution matrix, we will get the solution to our system of equations. So let's try one of these. Let's take the system of equations. 2x plus 4y plus 6z equals 4, negative x minus 4y minus 3z equals negative 4, and y minus z equals 0. Now, if we were to convert this system of equations into our matrix equation, we'd start with the coefficient matrix, 2, 4, 6, negative 1, negative 4, negative 3, 0, 1, negative 1, times the variable matrix, x, y, z, equals the solution matrix, 4, negative 4, 0. And now this is the Ax equals B matrix setup. If we can find the inverse of A and multiply it by matrix B, that will give us our solution. So let's write this out as an augmented matrix. Matrix A is 2, 4, 6, negative 1, negative 4, negative 3, 0, 1, negative 1. And then the identity 0, 1, 0, 0, 0, 1, 0, 0, 0, 1 with those diagonal ones. And now we try and find the inverse. First we need to get a 1 on the top left. It's a 2. We multiply by the reciprocal of 1/2 times row 1 to get our new row 1. Multiplying that row by 1/2, we get 1, 2, 3, 1/2, 0, 0. The other two rows are unchanged. Negative 1, negative 4, negative 3, 0, 1, 0, 0, 1, negative 1, 0, 0, 1. Now what we want to do is we want to find opposites to get zeros below and above the 1. In this case, the last row already has a 0, so we just need to work on row 2 by multiplying by the opposite, positive 1 times row 1, adding it to row 2 to get the new row 2. Well, that's nice. 1 times 1 is 1, 2 times 1 is 2, 3 times 1 is 3, 1/2 times 1 is 1/2, 0 times anything is 0. So when we make our new matrix, the top row is unchanged. 1, 2, 3, 1/2, 0, 0. The second row, when we add, -1 and 1 is 0. -4 plus 2 is -2. -3 plus 3 is 0. And 0.5 is 1/2. 1 and 0 is 1. 0 and 0. The bottom row unchanged is 0, 1, -1, 0, 0, 1. Now that the first column is taken care of, we want to get a 0. Whoops. Let me try again. We want to get a 1 in the center slot. Couple ways we can do that. We could do that by multiplying by the reciprocal, -1/2 times row 2 to get our new row 2. But I'm not going to do that because I see something that might be a little nicer. Notice the row below it has a 1. If I swap those rows, we'll have a 1 in the pivot point I want without having to create any more fractions than we need to. So I'm going to take row 2 and swap it with row 3. And let's see what that gives us. So the top row unchanged, 1, 2, 3, 1/2, 0, 0. The second row is now 0, 1, -1, 0, 0, 1. And the third row, 0, -2, 0, 1/2, 1, 0. Now that we've got that 1 that we want, we can work to get zeros above and below. In row 1, we multiply by -2 times row 2, add it to row 1 to get the new row 1. To get the third row to work, we multiply by the opposite, which is a +2, times the pivot row 1 plus row 3, and stick it into row 3 to get our new matrix. So first we're multiplying by -2. 0 times anything is 0. 1 times -2 is -2. -1 times -2 is +2. 0 times anything is 0. 0 times anything is 0. And 1 times -2 is -2. So our new row 1 when we add is 1, 0. 3 plus 2 is 5. 1/2, 0, -2. The second row is unchanged, 0, 1, -1, 0, 0, 1. The third row, we're multiplying by 2, the pivot row by 2, so 0 times anything is 0. 1 times 2 is 2, -1 times 2 is -2. Anything 0 times anything is 0, 0 times anything is 0, and 1 times 2 is 2. And we're ready to add those. We get 0, -2, and 2 is 0, -2, 1/2, 1, and 2. Getting close. Now we just have to do the last column, making that -2 into a 1. The reciprocal of -2 is -1/2 times row 3 to get our new row 3. So the first two rows are unchanged, 0, 1, 5, 1/2, 0, -2, 0, 1, -1, 0, 0, 1, and 0, 0, multiplying by -1/2 is +1. 1/2 times -1/2 is -1/4. 1 times -1/2 is -1/2. And 2 times -1/2, that's going to be -1. Now we'll focus to get zeros above the 1 by multiplying by opposites. We take -5 times the pivot row 3 and add it to row 1 to get the new row 1. Similarly, in the second row, we'll take the opposite +1 times row 3, add it to row 2 to get the new row 2. And this should be it. In the first row, we were multiplying by -5. 0 times anything is 0. 0 times anything is 0. 1 times -5 is -5. -1 times -5 is +5/4. -1 times -5 is +5/2. And -1 times -5 is +5. So that first row now is 1, 0, 0. 1/2 written with a common denominator. We're multiplying by 2. We get 2/4. So 2 plus 5 is 7/4. 5/2. And 5 minus 2 is 3. The second row, we're multiplying by 1. So 0 times anything is 0. 1 times 1 is 1. -1/4, -1/2, and -1 times 1 is -1. And so when we add there, we get 0, 1, 0, -1/4, -1/2, 1 minus 1 is 0, and the third row is unchanged, 0, 0, 1, -1/4, -1/2, -1. Just -1. And we finally have A inverse. The all-important A inverse that we're looking for is 7/4, 5/2, 3, -1/4, -1/2, 0, -1/4, -1/2, -1. We need to multiply A inverse times B. So give me a little more space here. A inverse times B is going to equal our solution matrix. So we're going to multiply by the matrix B, which was 4, -4, 0, I believe. Let's scroll up and make sure. 4, -4, 0. So when we multiply this out, it should give us our solutions for x, y, and z. So first row times the first column, we have 7/4 times 4 plus 5/2 times -4 plus 3 times 0. Second row times the first column, we have -1/4 times 4 minus 1/2 times -4 plus 0 times 0. And the third row times the third column, we have -1/4 times 4 minus 1/2 times -4 minus 1 times 0. And when we do that, what's nice is these 4's divide out all the way down. The -4's over 2 give us -2. That'll help make the math easier. So what we have is 7 minus 10 plus 0 is -3. -1 plus 2 is 1. And -1 plus 2 is 1. And so our solution for x, y, and z is x equals -3, y equals 1, and z equals 1. That's how we can solve a system of equations by using the matrix inverse. We find the inverse matrix, multiply it by the solution matrix, and that will give us the values for x, y, and z. So take a look at it on your homework assignment and bring your questions to class. We'll see you then.